next talk is given by Xavier Bonaventura from BMW and Jorge Pinto from Critical Tech Works. And they are touching a very, I hope, interesting topic, which is, you know, Peter has been telling you all the time, hello, Peter. Peter has been telling you all the time, unit test, unit test, unit test. But then when you write your unit test, I hope that you measure your coverage. How much is your coverage? And, well, we don't know, because the next question is, are you sure you are measuring properly your coverage? You probably use gcov, or perhaps not, and then you get a figure and you say, okay, this is true. And then Xavier and Jorge might have some news for you. You want this?
I will just stay here.
Okay, go ahead.
Okay, yeah, welcome. Basically, yeah, we are here to talk a bit about coverage and our experience. Basically, let's start a bit about us. I mean, I've been working in C++ since 2011, and basically I'm in safety critical systems, mainly autonomous driving, since 2018, and we had quite of right now, right, like a full release cycle for one whole project. And I'm representing BMW at the MISRA meeting, or yeah, I do my best. And basically I'm also in the C++ community meeting.
Yeah, so hello, all, I'm George. So I've been working with C++ since 2015 in safety critical systems related to autonomous driving also since 2020. And for this past few years, I've been the quality guy for the project. So I've been handling the topics related to static analysis, dynamic analysis, code coverage, what's on, and also the automation part.
Yeah, and basically, I like usually to set the ground that everything is clear. Like, we are not compiler experts, like no coverage experts. We work, like we had just these requirements of quite high code coverage. He was kind of like his team was more like setting the goals and providing the tools, and we had to make it happen. And then it's like we saw lots of issues in the middle. And basically what we want to do now here is like to share these thoughts and like lessons learned, something that at least, if you are in the same situation like us, that you have the machinery to at least understand. And maybe first I would like to start that we try to think about why is it important testing. I'm not sure how many of you know what is this image. This basically Arena 5, the flight 501 in 1996. This rocket took off, and around 37 seconds after taking off started like turning, like you can see in the image, in such a way that at some point basically it detached and basically triggered the auto-destruction and basically it just crashed. This is one of the examples that you might find around if you try to see, hey, why is it bad to have dead code, or but let's see a little bit what happened here. I mean, here, like the rocket, they integrated 39 seconds after taking off, and basically this was like, because you can clearly see in the image, it just take the wrong turn. And this was happening because you had the system in the Arena 5, you have two systems doing the calculations and then sending the information about what should be doing for correcting. And basically it was sending the wrong data, just saying you need to turn. And then basically the control was just turning. And this wrong data was because there was some operand error there. And this operand error was not properly handled. And this operand error was because there was a conversion from double to integer, 16-bit. I mean, it's like quite easy this to go wrong. Of course, then this was an overflow and was not properly handled, and will not go too much into details. And basically this happened because the input value was too high, and this value was coming from a sensor. And here you can have, I try to find the official links. These are the official links for the whole report, that if you want to I don't know, you grab a plane back home and you want to be entertained during the plane, that's the way you can just read it. It's quite interesting. But now let's see a little bit here what went wrong in different ways. The first thing is that the code was taken from Ariane 4, just kind of as is. And even more interesting, this code was like, that was sending the wrong signal, was not even needed during the takeoff. Like, this was code that was running on the rocket when you are standing on the platform, just to kind of correct, and then after takeoff it should not run. The thing is that there was a requirement from Ariane 5, from Ariane 4, that it had to keep running, but that was not needed in Ariane 5 anymore. And why this was not detected? Because like in the whole testing, it was not tested with the trajectory. Like this, it was just if someone would have put as an input the trajectory that was planned for the Ariane 5, they would have detected this error. This was just never tested. And why I'm showing you that, it's just, I mean, this is a case that you will see. I have my doubts that this was because there was not enough code coverage. If you have a case that you know that it's because you didn't have enough code coverage, let me know. This was estimated 370 million with some delays. But apart if this was a problem of code coverage or not, now let's go to then see that you can answer that question afterwards, if good code coverage would have solved the problem. How many of you measured the code coverage? Okay, quite good, quite good. How many of you have a target that is 85% or higher? But that's not so much. 95% or higher, okay? Still 4 hands, 5. And 100%? No one. And someone says impossible. That's very interesting. I will not then ask for higher than 100%. But basically, the motivation why I wanted to have this talk is because I think it was 2-3 years ago, someone came to me and said, you must achieve 100% code coverage with unit test. And that was exactly my reaction, like impossible, no way. Interesting enough, it's possible. I mean, you will pay a high price, but it's possible. But something must be wrong. I mean, and then for me, the first question is like, why? Why you want to achieve that? And what does it mean to have 100% code coverage? And that's the part that, let's just all go to that process. The first thing is like, what is code coverage? I mean, the code coverage is like percentage of code executed by a test. That would be a simple way to decide that. We can have here an example. Sorry for the string view, but it's a string literal, that's fine, not a problem. Here you have like, yeah, just probably like university exercise. You can do it in different ways, but let's say you have this switch statement, and basically you want to convert like a number to the day of the week, like from 0 to 6, Monday to Sunday, and you just want to give the string. Now let's see how we could test this code. Of course, if you would use test-driven development, it would have been the other way around, right? Like you would write first the test. But unfortunately, it's not happening everywhere, but let's just take it in this direction. Yeah, I'm not sure if this just to see it better. This would be one option. Basically, you just have several statements here. You just have the different values from 0 to 6, and basically you expect that what it returns is the string that, yeah, Monday to Sunday. And now here, basically, you have one last case that would be a value that is not in the range of 0 to 6 that give you unknown. Here we could discuss like if you still miss some other cases apart from 7 for the known case. But in general here we could say, let's roughly speaking, we have 100% code coverage. I would say it's good enough. I mean, I don't know like if someone would disagree, but I think I would be okay if someone commits that code with this test. But now maybe someone writes some other test. And this could be like another test that I could write. And basically it's like, I'm testing for the same input, like from 0 to 6. And I mean, basically because I know that this exists, well, it's like I know that needs to give me something different than unknown. I'm testing that, but just keep in mind, this could be that I only have this test. Just forget about the other one. Is that good enough? I mean, it's 100% code coverage. We are just executing all the lines. We are just checking all the places of the if. Is this good? Well, for me, no. That's bad. I mean, yeah, sure, like it kind of checks something, but that's not really something good. And here comes the point. What does it mean to have 100% code coverage? I mean, low code coverage means that you can do better. That's clear. Like, you can do better. But high code coverage does not mean anything. And sorry just to be so clear, but high code coverage means nothing. The only thing that means something is the low code coverage. And one thing doesn't imply the other one. The fact that you do not have low code coverage doesn't mean that, hey, perfect, everything is fine. And this is the first takeaway that I would like that you remember. Now let's go to the first test. We said that this was fine. Is it fine? Someone see a problem with this one? What if I would tell you that there's this requirement? Well, I mean, this test has 100% code coverage, but has exactly 0% requirement coverage. Because the requirement is telling you that, I mean, if you follow the ISO standard, it would be that it goes from 1 to 7, not from 0 to 6. Perfect, you achieve 100% coverage, but whenever someone asks you for that, you can just show that and ask them if they are happy with 100% code coverage. And basically, the takeaway here would be like, requirement coverage is more important than code coverage, but still, you should have high code coverage. I mean, it's like, again, that doesn't mean anything, 100% code coverage, doesn't mean that we don't have to have it, but that's not enough, okay? Like, we need to be careful here on the logical implications of all of these statements. Okay, then someone told to me, like, you must achieve 100% code coverage with unit test, and my first question was like, why? Sorry, I'm a bit of a rebel usually, and basically like I want to know why. And basically it was like, okay, we have the ISO 26262, this comes from automotive, and basically let's check, like probably somewhere in the ISO says that I have to have 100% code coverage, right? I assume. And basically the ISO, the chapter, the ISO 26262 is divided in chapters, chapter 6. There's this paragraph here that basically what it says, the part that it's more relevant, is that it says that at unit test level shall be determined by measuring a structural coverage, like the structural coverage should be measured, and according to certain metrics. Interesting enough, here doesn't say anything about percentages. The last sentence still says that if it's insufficient, like if the chief structural coverage is considered insufficient, that of course it's something that then you can discuss if having only 70% is sufficient or not. But let's check this table. And here we have three methods to measure code coverage. The 4 columns on the right, you don't have to care too much. If you don't know what it's about, it's more about how critical it is, your code. It goes to some categorization. But these are like the 3 methods that usually people use. And let's go over them. The first one is a statement coverage. A statement coverage is the one that probably it's more intuitively, the one that most of the people measure, the one that it's, yeah. Let's check what do we have here. We have the statements in this function body. We have one statement for the if. I mean, the if is a statement that we must execute. And then we have one statement for each of the two returns. That would be 3 statements in total. Now we can have a test that checks, calls the foobar function with the foobar set to true. And this will just, basically what we'll do, execute the if statement, and it will also execute the return foo plus bar statement. 2 statements in total. This gives us 66.6% code coverage. Clear so far? Let's go to the second one. That would be branch coverage. Branch coverage, the goal is that you cover all the branches in your code. This is especially important when you have error cases. Like, it's relatively common that you just test the nice case, but not the not nice case. And probably if you want to have some actions on the error case, if you want to trigger a log or terminate or something, probably you want to test for that. And that's what we are doing here, is just to analyze the branches. In this case, we have one if, and basically we have like one branch, one iterable waits to true, one branch, one iterable waits to false. This would be 2 branches in total. And basically with this test, then what we have is that in this case we execute only one of the branches, we would have 50% branch coverage. And now let's go to the last one. How many of you have heard about MCDC coverage or are familiar? Okay. Basically, MCDC coverage, there is there are different types. It's about measuring like the coverage on decisions, and you have different ways to do that. And with the modified condition decision coverage, you try to cover as many decisions with as least test, or like it's kind of an optimum point. Let's see how it works. Basically, the idea is like we have here a function that it's just to decide if we go to work or not. And let's decide based on 3 things. We could put other things there, but basically like we can decide if it's weekend or if it's national holidays or if you are feeling sick or not. And if it's like in case of the 3 things, then you decide, no, I don't go to work. And otherwise, then you would go to work. Now here, if we go with the MCDC coverage, the easiest way is like just think about the table, like what are all the possibilities that you end up in this, that this if ends up in one or the other branch. And basically we have like 3 conditions, these are 8 possibilities. And now what we need to know is like, if we want to achieve MCDC coverage 100%, how many cases we have to cover? And the easiest way to think about that is as follows. First, you just grab one case, any, whatever. And basically you have a test for that, and you set your expectations. Now basically what you do is like you grab, for each variable, you just grab the case where you only change that variable. We can start with the weekend. Okay, the weekend from false to true. We also test for this case. Now we grab the national holiday from false to true. We also test for this case. And now we would do the same for the last case, the feeling sick, from false to true. We also check for this case. And these are the 4 cases that you would be required to test if you want to achieve the 100% MCDC coverage. And these are, yeah, some. Okay, and now here the other topic that I would like to cover is about the baseline coverage, because a lot of coverage reports that I've seen, they never consider what is the baseline. I mean, the thing is that what we saw that with code coverage is like you have the number of executed statements divided by the statements to be tested. And here comes the point. What are the statements to be tested? What do we have to test? if we include the std vector, do I have to test all the code inside the std vector? Let's just grab here an example. Like here you have a main function. This will be a binary that uses two libraries, a bar library, a full library. And then here you have some test, this food test, that the goal of this food test is to test the full library. And for doing that, we decided to use catch2. And now here the point is like, what is our baseline? What do we want to test? And for us, this is very important because like what you want to test is what it ends up in the car. Like I don't care so much about the catch2 library, quotes. I mean, still you want to make sure that your testing library works. But for this purpose, let's say that we care about what it ends up in the target. That the other parts will follow a different process. It means that this is the baseline. And this is important for one reason. If you right now you have this picture here, and basically you have this full library, you create the full test and you run the coverage report, I would bet that most of you, what you will see in the coverage report will be like the coverage of the full library, but you will not see anything appearing in the report saying that the bar library has a 0% coverage. And this is important because it could be that you have the full library fully tested and it shows you 100%, but in reality, like you have much lower percentage because you don't have the bar library. And that's why you should double check that if some translation unit is not tested at all, just make sure that that also appears in the reports as 0. And there you could just also try to follow kind of a test-driven approach that first look at the reports and seeing that are 0% and then increment them, that you know that you're doing something. Okay, then I will give to George.
Thank you. So, yeah, during this process of achieving 100% code coverage, I mean, because someone told us that we need to, we tried out different tools, and we will talk a bit about like our experience using them. We also have like a couple of compilers in our project. We have client and GCC as those compilers, and we have a compiler, a qualified compiler for the target builds. And we experimented like some tools because it's not that you have to have like 100% code coverage during tests, but what ISO 26262 says is that you have to have structural coverage and actually branch coverage for our use case. And what the functional safety guys will tell you, it's you have to have 100%. Use some statistics about your code for profiling. Yesterday, I think Sebastian mentioned like the address sanitizer examples. You can also have some code instrumentation, adding some code to check if you are going to mark some memory regions, what's on, to check if you are accessing them when you should not, and code coverage. So here we have like an example of gcov where you actually add a counter to your code, so you can actually measure if that part was being executed or not. We also use different tools, and basically what they provide you is like, so instrument your binary, you get some intermediate files, but in the end you want to have like a nice report, right? So you can look into it, oh, I have 100% code coverage, I have 95, what's on? And we have gcov, I think this is probably the most known one. A lot of times it's used with lcov. And lcov is like a set of Perl scripts that actually takes the text output of gcov and gives us a nice HTML report. We use this a lot. llvm-cov, we started experimenting it also, and the source-based code coverage. We don't have much experience, but we got some nice results with it. gcovr, which can be seen a bit as, how can I say, an alternative to lcov, because it uses gcov under the hood, And it also gives you like HTML report, and it has some features that are interesting, and especially for us in the ISO 262 use case, we have some interesting features here. And then you have commercial tools. I put here 2 as an example, but we don't use them, so yeah. Now, hands in the air again, sorry guys. How many of you guys use gcov? Okay, a lot of people, okay. llvm-cov? No one. Oh, you, okay, nice. gcovr? Okay. And other tools, commercial tools, also. Okay, nice, okay. Maybe we can have a chat after, okay, cool. Okay, let's start dig a bit into the tools itself. So gcov, like basically when you instrument your code and use gcov, it will generate you some nodes files at compile time, and it will generate also some gcov data files at runtime. And the instrumentation is based on this profile arcs thingy. And we were like, okay, so what is this? And we checked, like, so basically an arc, we checked like it was a part of a control flow graph. So, I mean, the control flow graph will models possible execution paths through the program. So we have the basic blocks, which are sets of linear instructions, and they have no branches, and the arc connects 2 of these nodes, right? And if we take an example of this code here, we can actually check a representation of it. So we have it like here, the if statement, and then the 2 branches that it generates, 2 basic blocks, and yeah, this is like an if else statement. And yeah, here we have these GCNO files, the gcov node files. They'll be generated at compile time, and they will be helpful to reconstruct the basic blocks and map them to the source code. So actually, gcov will use this information and try to map it out based on the GCDA and the runtime data to get you the overall report. llvm-cov. We did not dig too much deep into this tool on the usage of it. This talk is really nice from Ala, and I recommend you watching. I mean, that's how we were introduced to it, and also the documentation is really nice. And here, I mean, for us, the nice thing was that the instruction to source mapping was actually done via the AST, right? So most of the times you have a really nice representation of the coverage. And also here, the counter allocation is done before the optimization kicks in. It means sometimes that even if your function button gets in line, the instrumentation will also be. So you will also get the information back, and you get a better view or a more comprehensive view on the report. The gcovr. So this was the feature that we really was nice for us to use, because we were having a lot of branches on some cases that we could not explain like at first view. And it was creating like really cumbersome reports, and we were mostly interested on like what's going on the decision level, right? I have an if statement, so what's going on here? And not so much about like branches generated by the compiler, what's on. And they have this option that actually can show you like these branches and mark these branches for you and get like your overall condensed report based on it. And it doesn't try to be too smart. So every time it could not analyze and determine if there was a decision there, it will just tell you. Now we have some examples of like each of the tool behaves. I'm sure you guys can get more examples of this. These were just some of the ones that we checked, and the tools behave differently. It's not that they are better or worse, it's just we got different reports and we try to understand why. So in this case, you just have a simple if here, some conditions inside, And yeah, just execute the function. If we use gcov, we'll get 4 branches. And why? And we started to ask, okay, let's check. We went to the CFG representation of the code. And we can actually see, okay, so we have a basic block here, we have an is, and then we jump to this basic block or jump to this one, and the same here. So we will actually have like 4 basic blocks. And so this is like a bit how we started to understand how the coverage was working. For the llvm-cov, since it's not based on the basic blocks, we only have 2 branches, and we can see it here. One, if this is evaluated to true, which never happens, or if it evaluates to false. But we got both marked here, and how the statement was evaluated. The gcovr. So most of the examples are related to the branch coverage, which were more problematic to us. Here you can see the tool is based on gcov. You have the branches here. You still have 4 branches, but decision level, you will just evaluate this, and okay, this part was not covered, this one it was. Templates. So here we have like just a function template. This is also something that the different tools give you like some different results. Not results really, but a different view. So yeah, if we, it's a bit an intermediate representation of the AST with GCC. We can also do the same with Clang. So we have here both of the template instantiations. And for gcov, okay, it's fine. We got both branches here, and it seems okay, like the data seems accurate. llvm-cov gives you a nicer view in some sense that you can actually, it will show you both instantiations. So you can actually check which one of those covered each branch. So yeah, we thought that this was really nice and really neat. And gcovr, based on gcov, is pretty much the same. This is was one of the examples that a lot of developers were complaining about, like why when we have like some static SED vector, for example, why we have a lot of branches. And we do, like for this line, on the report it appears like 8 branches, so it's actually a lot. Okay, why they are there? So, okay, we took a look into the CFG. Maybe like we were, okay, so we have some try to lock here, then we have some allocations, and this seems like an exception path maybe. So let's try to compile this with no exceptions. Okay, if we do compile with no exceptions, which we cannot do on our code base, but just to try it out, we got less branches already, right? We still have these 2 basic blocks here, and they are probably related to the static initialization part. So let's remove the static, just for an example. Okay, so here, we don't have it anymore, and you actually don't see the branches anymore. And this is not important, so, oh, we are going to remove like static and what's on and compile with no exceptions. It's just like for us to understand like the numbers that were besides this, that are not evident like when you first look into the reports. At least they were not to us. And yeah, llvm-cov just don't show you any branch here. I mean, and gcovr shows a lot of branches, but no decision, because effectively there's no decision being made here on our source code. Consespra. Yeah, this is also another example, right? So here we just have a simple function, we call it twice, and we see that it pretty much looks like it was not even instrumented, right? We have a condition here, and this was pretty much not triggered. Why? Okay, if we take a look into the CFG, we actually see that it was inlined here. So we got the values here, and gcov is not able to do the remapping again, it seems. llvm-cov does, and I think we did not dig deeply into this, but we really think this is because of the instrumentation also being in line when it is optimized away, so they can even reconstruct and give you the information back. So this was also really neat. And gcovr, it works pretty much the same way as the gcov, because it's gcov based and we have no branches, no decisions here. So yeah, I think that's it for the tooling part. Yeah.
Okay, then let's go with a final summary of the topics that we wanted to cover. As we said, high tool coverage does not necessarily mean high quality. Just keep that in mind. Don't forget about requirement coverage. I mean, that's something that if you would do TDD in the end, like you only implement requirements, right? Like you would end up like with a good requirement coverage. Always be aware of your baseline. When you go home, just make sure that what it appears in the report is really everything and you don't have something missing. A typical case is that probably the main doesn't appear, right? But you might have quite a lot of code in the main that maybe you want to test. And basically know your tools. Different tools produce different reports. Just understand the differences, just decide which one fits best for you. Depends on how critical is your code. But yeah, don't overdo. I mean, everything comes with the cost.
Yeah.
And yeah, that's it. Here we'll have some references that you can check, and if there's any questions.
So, questions?
In the result view, there was often written the value of the, I think slide 42 would be a good example, but
42, you said?
42, I think, yes.
Yeah, it's always the right one.
No, maybe 43.
Okay.
Yeah, here. So here it's written that it's true and false, below now, 2. Does this mean that there's no short circuiting? Because how does it know that the second thing is false when because the first was not true? I reword my question.
Okay, more questions?
I might not have paid well enough attention because haven't done things like that. One question I have is, any of the commercial tools, do they claim to provide you with information of path coverage? Like all possible paths through your code?
We don't need it for our use case.
The question a bit is more like, I mean, this is what we try to show with the generated branches, like what are all paths? Because like one thing is like what are the paths in the source code, and the other thing is like what are the paths in the assembly code, and these are two things that are independent.
I would consider the basic block view, not the shortcut evaluation is a separate branch.
Yeah, but not only the shortcut evaluation, right? Because like for example, on assembly, like it's the example with the static, for example, right? That
go back.
Here.
Yeah.
This one. That basically, like, I mean, here, do you consider that there's how many paths are here, basically?
Because of concurrency, there's the once check on the initialization, and you have multiple threads coming in, which doesn't exist in main, but nevertheless, that optimization of compiler, you will have a branch
Yeah, this one, for example.
This one.
Yeah,
Yeah,
this one you
left
can see.
branch.
I wasn't surprised by that.
Yeah.
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 Some people are surprised that that piece of code has branches.
Yeah.
I mean,
Yeah.
and that in the end, it's like depends on what you want to measure, right? I mean, it's.
Okay. Any other?
But on elaborate on that, I mean, it's like I'm not so sure, like if to always measure the branches at assembly level is the right answer, because like if you have constable, const expert, that might not end up into the assembly code, but still probably you want to measure the coverage of that. That's probably you have to go in some kind of hybrid approach.
Doing TDD, you would get into those problems.
Yeah, yes. I guess that you have the takeaway then.
Thank you for the talk. I just have a question more, like if you had any advice in this regard, particularly in terms of branch coverage, like how would you deal with cases where, for example, you have a system call and then you perform checking against the error that the system call returned? Do you have any particular advice, like if you cannot make this function call fail immediately, do you have any particular advice on how to increase the coverage in these cases, for example?
Yeah, I mean, that was really a regular nightmare. You have several options. You have, basically you can just kind of, at link time, you can replace your symbols, and then you need to be very careful there, because you go in a very dangerous territory where you can have UB at linking time, and yeah, that's one option. The other option is that you just have a wrapper, like all your system calls, you just have a wrapper with you have an interface for every single call. Basically, it's like kind of an operating system abstraction library, and that's the other option that you can do it. But there's no good way, like both options are bad. I mean, now you can tell me like, yeah, but I don't want to have the interface because of the overhead. You have the compilers that they provide you the devirtualization that might save you there. But all of these calls, and you said about POSIX, but like just grab about the file system from the standard library. I mean, how do you mock that? I would like that that C++ would be more mockable, but it's like, it would come with a price, right?
Thank you.
Thank you. Any other question? Thank you very much.
Thank you.